Build a single neuron that learns in Python. By the end, you will have a tiny neuron that computes a weighted sum, turns that into a probability, measures its error, and takes a gradient step to improve. You will see raw pre-activation scores, sigmoid outputs, per sample errors, a regularized loss comparison, and updated predictions after one parameter update. I'm Professor Pi, teaching AI foundations with Python, from basics to advanced. A single neuron teaches a core idea, minimizing mean squared error, which is the average of squared differences between predictions and targets. The payoff is clarity. You see exactly how a weight affects output and loss. The trade-off is simple: model capacity versus interpretability. This tiny neuron works on very small data sets and shows measurable shifts in predictions after one update. But it cannot learn complex nonlinear boundaries by itself. Think of the neuron as a smart weighted average followed by a squasher. It shines when the relationship is simple and roughly linear after a smooth transform. Its limitation is obvious. One neuron cannot model complex classes. Still, the mechanics you learn transfer to layers and larger networks. We will build a neuron that takes two feature inputs, computes a dot product plus bias, applies sigmoids to make a probability, evaluates mean squared error with an L2 penalty, and performs one gradient descent step to update weights and bias. This snippet computes a neuron's weighted sum on one tiny input. It defines a toy dataset X with two features per sample and matching targets Y. The list W holds the neuron weights and B is the bias term. The code picks the first sample X and computes Z as the dot product of X with W, then adds the bias to form the pre-activation score. The print statement shows that raw pre-activation score, which is the basic signal a neuron passes into its nonlinearity, and which determines how confident the unit will be before squashing. Next, we add a squashing function to make the score usable as a probability. This snippet adds a sigmoid activation to squash the raw neuron score. It defines the function sigmoid, which turns any input into a 0 to 1 output using the exponential function, and is useful when we want probability-like outputs. The code reuses the earlier Z and converts it into a smooth activation A. The sigmoid damps extreme values and stretches mid-range differences, so changes in Z near 0 have larger effects on the output. The printed value shows the neuron's probability-like output for the first sample and helps relate raw scores to interpretable predictions. Next, we will evaluate how well the neuron fits each example and find the easiest example. This snippet compares errors across samples and selects the easiest example. It computes raw scores ZS for every row in X using the current weights and bias. Each score is passed through sigmoid to produce predictions, and then it measures squared error against the target Y for that index. The list errors stores pairs of index and error value, and the code picks the smallest error using the minimum function. The printed tuple shows which sample fits best and the size of its error, revealing where the neuron currently performs least poorly and giving a quick diagnostic of model behavior across the toy dataset. Next, we penalize large weights to avoid overfitting by adding regularization. This snippet adds L2 regularization to the mean squared error to penalize big weights. It first turns current scores into predictions using the sigmoid formula, and then computes mean squared error, which is the average squared difference between predictions and targets. The term reg adds lambda times the sum of squared weights, so it discourages large weight values and acts as a complexity penalty. Increasing lambda raises the penalty and increases total loss, which often yields smaller weights. The printed pair compares plain loss to regularized loss, showing the trade-off introduced by weight control in a clear numeric way. Finally, we actually adjust the parameters with a gradient step and observe the new predictions. This snippet performs one batch gradient step and shows updated predictions. The helper F computes the neuron's sigmoid output using current weights and bias. The code builds the list of sigmoid outputs and then derives gradients for squared error by combining the prediction errors with the sigmoid derivative, which captures how output changes with score. Using averages of those gradients, it nudges the weights and bias with a learning rate of 0.8 to reduce loss. A larger rate moves faster but risks overshooting, while a smaller rate is steadier. The printed list reveals the new predictions, indicating a learned shift toward the targets after the update. Recap: it is a single neuron that computes a weighted sum, applies sigmoid, measures mean squared error, and updates by gradient descent. Use it to learn simple relationships, to debug training mechanics, or to teach how activations, loss, regularization, and gradients interact. One caveat: one neuron is limited in expressivity and cannot replace multi-neuron networks for complex tasks. Next step: expand the same pipeline by adding more neurons into a small layer and observe how the same loss and regularization ideas scale. Or alternatively, tune the learning rate and regularization strength to see their effect on training dynamics. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.